Todavía no. Yep. Micrófono.
Buenos días a todas y todos. Por desgracia, hemos llegado al último día de la escuela. El día de hoy les voy a compartir la agenda para el día de hoy. En unos momentos el doctor Michael Dickey dará la tercera sesión del curso sobre metales líquidos y después tendremos un breve receso. Posteriormente será turno de la doctora Sandra Rodil con la tercera sesión del curso sobre evaluación fotocatalítica de semiconductores. Al término de este curso será la clausura del evento. Entonces, sin más que decir, le cedo la palabra al doctor Michael Dickey. So, good morning, Michael. Thanks for being here in this third session. So, yeah, it's all yours.
Thank you. Okay, can you see my PowerPoint?
Yes.
Yes.
All right, great. Okay, well, buenos dias. Good morning. It's really lovely to see all of you this morning. Thank you for coming back. I'll take that as good news. Today, I'm going to talk about something different than liquid metal. So I'm going to talk about some other work from our group that I think you'll enjoy, at least I hope you will. And it has to do with polymer sheets and converting them from 2D, two-dimensional, to three-dimensional. So I'll just jump in. So basically, what I'm going to be talking about is starting with flat surfaces. And there's a number of reasons why you would want to start with a flat surface to ultimately make a three-dimensional shape. One of the reasons is that flat sheets, particularly of polymers, are very easy to make on a commercial level, very high throughput. So they tend to be inexpensive. If you can make something flat, you can stack it up and ship it in a very efficient way. It's very expensive to ship air, where it's kind of wasted space in a container. So if you can ship something flat and then assemble it, then that's desirable. And I don't know if you have the furniture store IKEA, but they're sort of famous for this, for taking furniture and putting it in a small box, and then you put it together and it becomes a chair or something like that. And then another thought here is that there's a lot of processes that are designed for flat surfaces. So for example, inkjet printing. Inkjet printing works really good on paper or other flat surfaces, but it does not work good on a curved surface or a topographical surface. Likewise, the way computer chips are made, they use optics using light that is focused down onto a 2D plane, two-dimensional plane. And so the way that electronics are made are also on flat surfaces. So if you can make a process that can, use some of these two-dimensional techniques and then ultimately use that to make a three-dimensional object, that could be very interesting. So there's a few examples here just kind of from everyday life. This is a piece of furniture that folds flat, and then it can unfold and become a chair. This is a piece of plastic that has been folded to become a package for storing something. These are electronics devices that have been produced on a flat surface and then molded into a three-dimensional shape. And then this is just kind of a fun example, but talking about implantable or deployable devices that can ship very compactly and then either be assembled into 3D or expand somehow by changing their shape. So there's a number of ways that people have done this using polymers, and I'm going to show you just at a very high level what those are. So this first approach is using very basic molecular principles. And so in this particular example, these are called liquid crystal elastomers. So elastomer means rubber, like stretchable material. And then a liquid crystal, you probably have heard this term from a liquid crystal display. So these particular materials, the molecules they're kind of like crystals in the sense that they line up like this. So you can actually direct which way that they line up, sort of like a crystal. But when you heat them, they will become disordered. And when they become disordered, that takes up more volume. And as a result, it creates stress that can be programmed to go from a flat surface to one that has some topography. And the way that you do that is you dictate how little pixels of the material are aligned. So some of them are aligned this way, some of them are aligned this way. And that dictates how the stresses are generated inside this material. Probably the simplest way to get a material to bend or to fold is to use what's called a bilayer. So bilayer just means you have two layers that are stuck together. And when you heat them or you swell them in water, they will expand at a different amount. And that creates stress, which causes these things to bend. So this is fine in the sense that it's very easy, but it's really slow. And it also results in not very sharp folds. It results more in like a bend. So there was some really nice work about 8 years ago now that used these materials that can swell. They're gels, hydrogels, and they were patterned with light. So this is showing a mask using little holes to create regions where the light can hit the material, and wherever the light hits the material, it becomes stiffer. So each of these little black spots is a highly cross-linked polymer. So it's a polymer that cannot swell. And depending on where you put these dots, you can get the material to swell in different ways. And so this is a really nice way to control the way a material is going to respond to swelling. And then there's another approach, which is called shape memory polymers. And I'm actually going to be sort of talking about this today, but in a different way than is conventionally done. So with a shape memory polymer, you actually will start with the shape that you want, which is the three-dimensional shape. In this case, it's a box. And then what you do is you heat the material and you stretch it to some flat states. So you start actually here and you stretch it and heat it, and then you cool it down so that it stays in this shape. Then when you heat it back up, the stresses that are built into those materials will cause it to fold. Okay, so there's a bunch of ways to do this, but each of them has different advantages and different disadvantages. What we tried to do, and this is moving to our work, is we were trying to use 2D patterning to make three-dimensional shapes. And so what do I mean by 2D patterning? So these are some examples. So one example is so-called roll-to-roll manufacturing. This is the way that newspapers and magazines are printed. Inkjet printing, I think we all know what that means. And then lithography. So lithography refers to the process that's used to make computer chips. Again, it's using light with a pattern of light that gets focused down onto a surface. And then the surface is covered with a photoresponsive material that will respond to light. So anyway, what these all have in common is that they are two-dimensional and they're very inexpensive on a per pixel basis. Okay, so I've said a lot of words, but let me show you a fun video. So this video sort of captures the main point of what I'm hoping to show you today, and that is we've got this really simple piece of plastic. It's actually polystyrene. It's the same polymer that's used in styrofoam and petri dishes and maybe in your laboratories. And on it, there you can see there's some black ink. Well, this whole thing is sitting on a glass slide and sitting on an aluminum foil, which is not important. We're then going to take a very inexpensive light bulb, actually an IR light bulb, and shine it on this. And as you can see, the whole thing folds. So in case you missed it, I'm going to show you it one more time. So here is our sample. We're going to shine light on it, and it very quickly folds into a box. So we're going from 2D flat to 3D a box. Okay, and so the materials that we're working with are called thermoplastics. So these are plastics that when you heat them, you can deform them. And so this is, we call this self-folding because we're doing folding without our hands. And the basic idea here is very, very simple. So we have these polymers, which we actually buy. They're polymer sheets, and they're pre-stressed. This is a key idea. Pre-stressed. So that means that when they were manufactured, they were stretched. And if you take these sheets and put them into an oven, they will go from this initial shape, this blue square, and they will shrink about 50% in the Y direction and 50% in the X direction. And as you can see, they get smaller, but it also gets thicker and a little bit rough, and it's less transparent. So the temperature where this happens is called the glass transition temperature. This is the temperature where polymers start to get soft. So instead of heating them up in an oven, instead what we do is we take these sheets and we pattern them with ink. So this is a computer screen, and this is a printer. So the black ink is literally from a printer. This is very, very simple. Anybody can do this. And so then we shine light. And the key idea is that the black region with the ink absorbs the light and it gets hot. And as a result, it shrinks. And when it shrinks, it causes it to fold. And of course, you can put the ink on the top, and you can also put it on the bottom of the sample. And either way, it will always fold towards the ink. So you can see that in this video. So this sheet actually has ink on the top and the bottom. And you can see that it folds into kind of a more complex three-dimensional shape. All right, so the key idea, the thing that makes this work, again, is its temperature. And we're just using light to deliver heat to the sample. So if you take a very simple sheet of this polymer and you put black ink on it, which is shown here in red, and then you shine light on it. Now we're looking at this with an IR camera. You can see that when we shine the light, you can see that it gets hot. And if we plot the temperature on the surface as a function of, well, this says pixel, but this really should be distance. You can see that in this red region, that the temperature is hotter by quite a bit, about, well, what is that? About 30 or 40 degrees Celsius. And the glass transition temperature of the polymer is about 100. So what we're doing is we're taking the polymer and we're heating its surface above its glass transition temperature, but only in the region where the ink is located. The rest of it is below the glass transition temperature and remains stiff. Okay, so these materials, they're actually children's toys, believe it or not. They're called Shrinky Dinks. And what people normally do with these is they take some initial shape, and when you heat it, you get some final shape. And honestly, it's kind of boring because it starts out as a square and it ends up as a smaller square. What we're doing is taking that same initial shape, and depending on how we pattern it in 2 dimensions, we get a variety of different 3D shapes simply based on the 2-dimensional patterning. These experiments are really easy to do. You can easily do them at your home. So for example, you can buy these sheets. You can buy a pair of scissors, which you probably already have. Instead of an inkjet printer, you can use a Sharpie or some black marker. And the light bulbs we use are maybe $10 or a little bit less. And so, this whole experiment is very, very inexpensive, especially since most of these things you buy one time and then you're done. So these light bulbs are called IR light bulbs. They actually produce visible light too. You can see them, and you could see it in that video. It's kind of have a red color, but they also produce infrared wavelengths that you can't see. And so these are the type of lamps that are used to heat up food, like at a restaurant. So after you cook the food, they put it under a lamp to keep it warm. So that's just a very common light bulb. So we've done this mostly with polystyrene, which is, again, we get it because it's commercially available, but we've also done this with different polymers. So this is a methyl methacrylate. It's acrylic, polystyrene, polycarbonate. So these are all different, very common polymers. And the key idea, again, is that the materials have to be stretched. We've done it with different amounts of thickness. We've done it with different amounts of strain and different amounts of time. And you can see that if you use like a polycarbonate material, this is like a material that would be used to make an airplane window that's very tough, not going to break, very strong. You can see that it can withstand quite a bit of force. Okay, so I told you some of the things that this might be good for, but there's some demonstrations that have actually shown that this is useful. So let me show you two of them that I think are kind of interesting. I'll start with the bottom one because it's moving and it's probably capturing your attention. So this was some work from my friends at Harvard, and they took the idea that I showed you already, which we had published, and they used it to make a robot that essentially starts flat and then it folds into a robot. Now you can see it's not completely 2D. It's got this battery on its back and there's some motors, but the assembly itself of the robot is simply by heat. Here, instead of using light, they're using joule heating. So they're running electricity through a conductor that causes it to get hot, exactly where they want it to fold. So once this thing folds and assembles, it can actually move and run away. So the basic idea is you're using all two-dimensional processes to make these things, and then you have the whole thing assemble and do something. In this case, it's a robot. One other example, I don't know if I can stop this video. So if you would maybe direct your attention up here, this is the same material, this polystyrene material, and it's attached to metal. That metal is actually an antenna, and when you shine light on it, the antenna changes shape, and when it changes shape, it changes its properties. So again, I talked a little bit about this on Wednesday, but this idea, if you can change the shape of a material somehow in response to a stimulus, you can change its utility, its use. Okay, so a couple details that I want tell you about how this works. So what we did is we said, okay, what if you want to control the angle of this thing, the way it folds? Well, we assume a couple things. First is at the top of the hinge where the black ink is, it will shrink completely, and the bottom hinge does not shrink at all. And when that happens, if this is a cross-sectional view, so this H is the thickness of your film, and W is the width of that black ink. So when the top part shrinks, it gets smaller and it causes the material to fold. And you can just use simple geometry to figure out what that is. And this is what we see. So this is the angle, which is defined right here as a function of the width of the black ink. And the black is the theoretical model, I should actually just say geometric model. It's very simple. And the red is what we actually see. And you can see that it's in pretty good agreement. We start to get a little bit of deviation around when it reaches 90 degrees, because if you imagine as this thing starts to fold like this, if it goes beyond 90 degrees, it actually will block the light from hitting the sample. And so a lot of these samples will fold to 90 and pretty much stop because the light is not reaching the hinge anymore. Okay, so this was a really simple model. This is just using geometry, and it's kind of good enough. But we went in and we did this a little bit more carefully. But it's actually quite a hard problem, and let me try to explain why. So here is your sample, which has the ink on it. And when you shine the light, think about all the things that are changing as a function of time. First of all, the temperature as a function of time and position. So it gets, if you pick any one of these points, the temperature is going to be changing pretty much at any given time. Since the temperature is changing, the mechanical properties change. Remember also, as you heat it, it can shrink. And so that's also changing, which is changing the shape. And then if it shrinks, it also changes the thickness. So this is a really good problem for what's called finite element modeling, where you break up your material into little small pieces and you model physically what happens to each one of those little things and how they interact with each other. And so this is kind of what it looks like in the model. I'm not going into a lot of details, but in the end, we were able to model the angle quite a bit better than just using simple geometry. So again, we did some mechanical measurements of the polymer, measured the temperature profile as best as we could, and that tells us, using this model, this mechanical response. So this was a collaboration with some of my friends in mechanical engineering. And the thing that was really satisfying is if you look at the hinge where this thing is folding, so you can see these are the panels and it folds right here. And of course, if it's shrinking, if it shrinks this way, it's going to get thicker this way. And so this is what we see experimentally. And then in the model, we basically saw the same thing. And if you're being a little bit skeptical, you might wonder, well, why is the model not symmetric? Like, why wouldn't it be perfectly smooth? And the reason is that when the sample folds up, its thermal environment actually changes. It's no longer in contact with the substrate. It comes up, and now it's in contact with the air. So we actually can pick up on that asymmetry simply by, well, it's not simple, but by using this model. All right, so thank you for bearing with me. I know I kind of went a little bit into the details, but let me show you some of the other kind of neat things that you can do. One of the things is that in the prior work, I showed you this is a cross-sectional view of our sample with the black ink. And we're basically, previously we were shining the light everywhere and localizing it using black ink. Instead, another approach to do this is to put the black ink everywhere and shine the light only where you want the heat to go. And so this eliminates the need to inkjet print at all. So this is the experiment. So here is our sample. And you can see that it's black so that it will absorb light. And you can't see it, but somewhere over here, there's a laser. And the laser goes through this lens and then through this lens. And then there's this thing here, which is blocking the light. So the student is going to go in and remove this. And so the light will come through and hit the sample right here. So please focus right here. It's very fast. So you can hear that was a good day for a graduate student. You can hear the response if you listen to the audio. So they said, oh, or whoa, or something. Anyway, you can see that this thing folds very fast. And all we're doing is moving a laser back and forth across the sample like this to get it to fold. Okay, so I've shown you using light. You can use other sources of heat. I mentioned joule heating. We've also done this with microwaves. This was kind of a fun project because we put a lot of things in the microwave that your mother probably told you not to. So we made a lot of sparks, and it was probably a little bit dangerous. But in the end, we found that graphene is a really good absorber of microwaves, like really good. And if you put these graphene inks on these materials and you expose them to microwaves, they will get hot and fold. And so depending on the width of this region, which is labeled W here, you can go from 0 folding all the way up to 100, almost 180 degrees of folding. So this was kind of neat, and this happens really, really fast. Now, one of the problems that we ran into is, and you maybe can pick up on this, is that everything we're folding is very simple, like just a single line. And if you want to do, let's say, more complex origami, the sequence of folding is very important. So, for example, if you, let's say you want to pack up some luggage to go on a trip, you know, there's a whole sequence. This is the first step, second step, third step that you use to fold this. And, you know, so this is sort of a practical application where sequence is very important in what we do. You can also do this for origami. And there's this guy, Robert Lang. If you're interested in origami, I highly recommend you check out his work. It's remarkable. He can take a flat piece of paper, and using this software that he developed, he has a PhD. He's a just brilliant guy. He actually quit his job. He worked at in California at the Jet Propulsion Lab. He quit his job to fully pursue origami as a career. And he developed this algorithm that will allow you to figure out the folds. So you can see here, these are the fold patterns needed to make a complicated 3D shape. So this, for example, he's been able to make things like a scorpion using only one piece of paper, which is absolutely remarkable. But anyway, when you do this, the sequence of folds is also very important. And then, of course, there's, even at the molecular level, folding is important. So there's, you know, proteins and DNA, the way that they're folded impacts their function in our body. And so if you have a misfolded protein, it's really bad news. It can make you very sick, and it, you know, maybe won't do its function. Okay, so how do we do this? Well, we can't do anything as complicated as I'm showing here, but we've taken a step in that direction using color. So previously I showed you samples that had black ink. Here the samples have yellow and blue as an example. And the idea is if you shine red light on the sample, only the blue will absorb it. And then if you shine blue light, the yellow will absorb it. So you can actually get it to fold in sequence. So if you shine the blue light first, you'll see the yellow will fold. And then if you shine the red light second, then the blue will absorb it and it will fold. And you're not just limited to these limited colors. There's sort of a number of different combinations that work. So let me show you the video just to give you an idea. So in the top right, you can see the color of the hinges. And then the color of the light is very obvious. So here's the same sample exposed to two different colors of light. This is just showing that you can extend this idea to other colors. And this is to show that we can, you know, fold things in order 1, 2, 3. This one's a little bit different. So this one, you can see the color of the light didn't change. So what we've controlled here are the color of the hinges. So this black one absorbs the light the most effectively, then the gray one, and then the red. So that's another sort of trick, is to control the absorbance. Okay, so again, so this is starting to control sequence, but we have only been making very simple folds. And so we started thinking, well, maybe we can actually use the ink over more of the surface to make curved shapes. So to study this, we made samples, very simple, just a rectangle, and we covered them with 50% ink. So in this first sample, we put the ink on the outside of the sample. And then on the second one, we put the ink on the middle. And so it's the same amount of ink, it's the same rectangle shape, but you're going to get very different results. So first of all, this is the sample with the ink on the outside. And when we shine light, you'll see that it first folds, and then it will curl, because that black region is trying to shrink. And so the shrinking causes it to fold, and then it causes it to curl. Then you can put the black ink in the middle. And when you do this, it will also fold, just one fold, and then it will fold, curl in the opposite direction. And so this is kind of exciting, because simply based on how we put the ink on the surface, we can get very different shapes. So these actually have technical names. One is called synclastic and anticlastic. I'm sorry, I didn't make up these words. I don't use these words in my day-to-day life. But they describe the shapes that we form. And you can see, again, depending on if you put the ink as shown in this column versus this column, you end up with two completely different shapes. So, all right, so this is fine, but the shapes that we form, in my opinion, are not all that useful necessarily. And so we wanted to do something a little bit more challenging. And this gets to the so-called map makers problem. So the map makers problem refers to, like, if you want to take the Earth, which of course is round, at least I think it's round, and you want to represent it on a flat surface, you have to distort your map somehow. And so it's called the map makers problem. And the opposite problem is try to take a sheet of paper, which of course is flat, and wrap it around a ball. So for example, if you want to, for a holiday gift, try to wrap a football with paper, and you'll see that you can't do it. You can't do it in a way that makes a nice, smooth sphere. Well, in our case, we actually can cause these wrinkles to shrink. We can make them go away. And so we do this by connecting two circles with ink on them, and you'll see here, it folds on itself, and then it continues to shrink. And those forces that are involved cause it to become a sphere. And so this is really difficult to do with most materials because of the requirement for it to shrink in a very controlled way. And so we're currently trying to model this and try to understand exactly, we did this just sort of through trying a bunch of things. And now we're trying to go back and figure out exactly why it works, which is probably the opposite way of doing things normally, but it's a good problem to have. All right, so now I'd like to show you some fun examples of where we think that this could be potentially useful. So I have two examples to show you. The first one is making grippers, something that can grab. And the second one is using corrugations to change mechanical properties. So for grippers, this is actually a really kind of hot topic in the literature right now, is to try to make sort of artificial hands that can pick up complex objects. And I'm going to show you here kind of three different ways to do this. One way is to use pneumatics, basically using pressure. And so you can see in this example, there are some tubes, and those tubes are applying some air pressure, which causes this thing to expand and therefore fold. This is really kind of a simple and elegant approach because this whole thing is made out of soft materials. We published a paper, and I'm going to show you this in just a minute, where we've used hydrogels where they swell in water. And this works, but it's very, very slow and not very strong. Another really clever way to do this is to use jamming of particles. So this is a piece of rubber, like a balloon, that's filled with particles. So imagine like sand, and that it's very soft. And so when you push on it, when you bring it on some object, it will, because it's soft, it will wrap around it like that. And then they pull, these folks, they pull vacuum on this, and that causes the balloon to tighten around those particles and cause it to become very stiff. So this is called jamming because the particles are basically all pushed together and jammed together. Well, what these all have in common is that they only grip when you're applying a stimulus. So for example, in this example, you have to apply pressure. In this example, you have to use water. In this example, you have to use vacuum. And when you take away that stimulus, the gripper doesn't work anymore. So what we've done is to use our folding, these plastic sheets, and as you'll see in this video, we can get this to, depending on how we put the ink, we can get this to sort of wrap itself around an object. Now, what makes this a little bit, there's two things that are interesting here. One is that when you turn the light off, it stays in that that shape. That could be good, that could be bad. In a way, it's good because it means you don't have to constantly apply energy. So if you want to have a permanent grip, this is good. If you want to reverse it, you can, but it's difficult for it to go back and forth without doing some tricks. The second thing is that these are made out of thermoplastic materials that are very strong. And so we've gone in and if you go think about that previous video, that piece of plastic, little piece of plastic is wrapping around a bolt. And at the top of this, screen, you can see that the polymer has gripped around these bolts, and these are pieces of wood. This one is about almost 2 kilograms, and was able to hold it for days. So that ends up being about 24,000. It's able to hold 24,000 times its weight. So the failure mechanism is actually suggests it could go even higher. So in this video, it shows that if we take this thing and kind of pull on it, you'll see that the stress goes up. We're pulling, it's going higher and higher. And at some point, one of those little grips will kind of break off, but it's still stuck on that bolt. And the way that it actually ultimately fails is the little piece of metal that we put on there to grip it will actually tear through the material. So if we had a better way to grip it, it probably would even go higher. But this is pretty good. 24,000 times its own weight. That's really, really good strength. Okay, another example is taking flat surfaces and making them corrugated. And so this is used all the time in our day-to-day lives. So if you think about a metal wire, it cannot be stretched. So you call this inextensible. But if you wrap it into a certain geometry, like a spring, it becomes very soft relatively soft and stretchable. Likewise, if you take a metal and you make it really thin, it becomes kind of flexible, just like if you have a piece of paper, because it's thin, it's quite flexible. And that basically scales, the flexural stiffness scales with the length cubed, the thickness cubed. And so one way to make this stiffer is to corrugate it. And of course, we see this in our day-to-day lives. So if you think about a corrugated roof, this is just made out of fairly thin metal, yet it's quite strong because of these corrugations. Likewise, you can make materials to be stretchable simply by their corrugation. So it has everything to do with which direction you're applying the stress. So in these very simple polymer sheets, if we corrugate it in one direction, we can make it to be very stiff, like 300 newtons or actually even higher. And if we corrugate it in the other direction, we can make it to be very soft and even stretchable. Okay, so let me show you the stretchable part. So these are the corrugations, and as you might imagine, we make this using light by shining light on the sample, and it's stretchable. So you can see you can stretch it pretty far, and eventually it will break. But when we do this, you can see that we can go so a strain of 0.5 means about 50% its original length. So, that's it's a polymer like this pen. It's hard. If I pull this, I cannot stretch it. But because of the geometry here, we're able to actually stretch it. And we have studied this as the function of the different corrugation geometries. And well, I don't think I'm going to spend any time talking about this, but it's just to say we can tune how stretchable it is based on the geometry. This shows just kind of a comparison, just to give you an appreciation for the change here. And so you need to compare this. First of all, you need to understand that this plot over here is referring to just the flat sheet. So it's like, imagine taking this piece of paper, grabbing it and pulling on it. And as you might imagine, when you do this, it goes to a very small strain, about 5%, and then it will break. And you see that the stresses required to do that are very high, so hundreds of megapascals. When you do the corrugations with the exact same material, now you can go to about 10 times more strain, about 50% or even higher. And if you notice, the stress is now orders of magnitude lower. It becomes effectively softer. So it's like 0.6 megapascal, whereas over here, it's like 100. Okay, so we've basically found well, this is not surprising. When you corrugate something, it makes sense that it's like an accordion, it should be softer. But the cool thing here is that you can do this using light. If you go in the other direction, so you corrugate it in the other direction, you can see that these things become very stiff, which is remarkable because these sheets are only 300 microns thick. That's about the size of a human hair, a little bit thicker, but not much. And you can see that when we compress this is the compressive strain. The load shoots up, and we actually reach about 500 newtons. And at that point, we have to stop because otherwise it could break our instrument. And so these things are very, very stiff. So anyway, these are just a couple of applications that I think are exciting where we've used changes in the surface shape to cause very big changes in mechanical properties of these materials. Okay, the last thing that I want to show you is some work that that uses kind of a different principle. And so in general, we wrote a review a few years ago that you might enjoy. It's listed here. And the idea is if you start with a two-dimensional sheet, there's a number of ways to give topography or shape. Bending, we've talked about. Folding, we've talked about. There's conventional microfabrication, like the way that computer chips are made. But you can also induce some surface topography. And I'm going to show you an example. So wrinkles, of course, we see these all the time in our day-to-day lives. We tend not to like to have wrinkles on our face. I actually think that this woman is quite beautiful with her wrinkles. And scientists have been interested in trying to make these types of wrinkles onto surfaces because they can do a number of interesting things like change optical properties, wetting properties, tribological properties. Okay, so this is just a picture from the literature. This is not our work. This is just to show how wrinkles on a surface, these wrinkles are aligned, and so it changes the way that this water droplet wets the surface. Normally it would be a nice, it would wet uniformly, like it would be round everywhere, but you can see on these edges, it actually takes on a straight shape. So the way to make wrinkles in general, including on your face, is by having a stiff film. So this could be a metal film or some polymer or something on a soft substrate. And they need to be attached to each other. And when you squeeze them, when you push down on them, you will form a wrinkle. And so this is sort of obvious. So I don't know if you can see this, but this is a piece of paper, which is stiff. And if I squeeze it, it will buckle. It will do something like this. Now, if you attach that film to this soft substrate, instead of making one arch, it will make a bunch of little ones because this represents the competition between elastic energy and flexural energy of distorting that surface. All right, so turns out this is really easy to do. And if you just take let's say a glass slide or a silicon wafer and you put a polymer film on it and you coat it with a thin layer of a rigid material like gold, for example, and you heat it, well, those two materials have different thermal expansion coefficients, and that is enough to generate stress such that it will actually form these wrinkles. This is what they look like. They kind of look like spaghetti on the surface. And so, a lot of people have studied this, and we are not the first people to do so. What we tried to do was to use light to control where these things form. So here's the idea. So this is another really good lesson for students that you'll see that like sometimes, maybe your advisor comes up with some idea and they might be wrong. So this was an example where I was wrong, and I'll show you. It's turned out to still be very interesting, but the idea was we were going to take a glass slide or a silicon wafer, which is called substrate here, coat it with polystyrene, which is very easy to do by what's called spin coating. Basically, you put some liquid on there and you spin it, and then it coats it very uniformly. And then we coat it with aluminum. If we put this whole thing in an oven, it would wrinkle. It would form those wrinkles. But instead, we're going to put some black ink on the surface and then shine light. And wherever we shine light, as you know, this black ink can get hot, and this should cause it to form wrinkles. Okay, so let's take a look and see what happened. So here's our sample, and you can see the black ink. And when we did this experiment, we shined the light on it, and you can see that the wrinkles were forming here. This is the aluminum region. So if I go back, instead of forming here where we thought that they would form, they formed here. And when we remove the black ink, you can see underneath it, there's basically no wrinkles. So this is, it's exciting because it means that we can dictate where these wrinkles go. We can put them here and not here. But it was really confusing because they were not going where we thought they should go. So we then did a very simple experiment. And we said, okay, let's take our film and let's heat it on a hot plate. And if we heat it above the glass transition temperature of the polymer, which is about 100 degrees, we get wrinkles. If we take the same film and we apply IR light, it actually gets hot enough to form wrinkles. So what that means is you don't even need the black ink. And so then the question is, well, why is it not forming where the black ink is located? And this is where I was wrong. What is happening is that the ink is actually sufficiently stiff that wherever you put the ink, it actually prevents it from forming those wrinkles. The wrinkles actually form in the places where there's no ink. So then if that's true, based on our hypothesis, if we put a soft ink, so it's the exact same structure, but it's softer, then we should be able to get wrinkles wherever we put the black ink. So indeed, the black ink from like an inkjet printer is sufficiently stiff that it prevents wrinkles from forming. So this is what the surface looks like before we shine the light. And then this is what it looks like after we shine the light and remove the ink. And you can see if you zoom in that the wrinkles are only forming in these like little squares, and they're not forming in the space between them. So this is, it was kind of interesting. And then we did the experiment with the soft ink. So this is silicone, which is soft, and we made it black by mixing it with some carbon particles. And you can see that when we shine the light, we used a different light source here. Actually, we use an LED. Nothing happens here. And then something is happening here. You can see it looks a little bit different once we remove the silicone. And if you look underneath it, sure enough, there are some wrinkles. They're not quite as pronounced, but they're there. Okay, so I have actually, I think just 2 more slides, and it's going to be slight change of the story here, but the last little bit is about actuating a different type of polymer. So instead of polystyrene, these are hydrogels. Hydrogels, what this word means, hydro is like water, and then gel refers to a gel-like material, and that's kind of a generic word. And there's a picture of a hydrogel here. Hydrogels are used in a number of applications. They're all around us. Our bodies are essentially hydrogels. Jello is a food. Gelatin is like a hydrogel. Contact lenses tend to be made out of hydrogels. And so these are these like soft, squishy materials, and they're basically polymer networks swollen with water. There's a lot of interest in trying to be able to get these things to make grippers. And one of the inspirations for this is an octopus or even like an inchworm. These are creatures that are made entirely out of soft materials. There's no bones or anything like that. And yet they can do these really complex tasks. And so this is a collaboration with one of my colleagues, Orlin Belov. We developed this technique called ionoprinting. And actually, let me start it over. So in this video, this is a piece of gel, and it's sitting on aluminum foil. And then this is a penny, which is a source of copper. And we apply a voltage to the penny. And when we're done, you can see when you remove the penny that we've transferred that green color into the polymer. So we call this ionoprinting because we think that we're printing ions in the gel. So this is the basic idea. This is the hydrogel. And the hydrogel is, again, it's mostly water. Like, I don't remember the number, but it's like 90% water. It's remarkable how much water these things can hold. And it's held together by polymers. So that's what I'm depicting here with these lines. And it's important to note that these polymers are ionic in nature. They have these sodium groups that allow us to do this technique. And so then we contact the gel with a copper, which again is like the penny, and we apply a voltage. That voltage converts the copper metal into copper 2+, which is kind of looks like Statue of Liberty, kind of that green color. And as you'll note, in this drawing here, there's 2 sodium atoms, and they're charged with same charge, but we've replaced 2 of these with 1 copper 2+. And because it's 2+, it acts like a crosslink. It interacts with this chain, and it interacts with this chain. So it actually will pull them together, and it makes it stiffer. So this effect can actually generate stress. Basically, it pulls those polymer chains together. Now you can see that it replicates not only the color that you would expect, but it replicates the topography or the shape of the penny. And that's because those copper ions bond so strongly that they don't diffuse away. Normally, when you put ions into salt, they will just solvate and they'll diffuse away. These stay in place for like months at a time. It's really remarkable. And so we've used this to create stress. And so instead of using a penny, here we use a copper wire. We apply that voltage on that soft material. And again, those copper ions generate stress, which cause this thing to fold. It's not super fast, but it happens on the order of seconds. So you can see that the angle propagates to about 90 degrees in a few seconds. We can actually reverse this by removing the copper ions, which you can do using a so-called chelating agent. It's a chemical that will remove the copper. Ideally, we would like to do this electrochemically, but we have not done that. So you can use the stress that's generated at one of these wires to create a gripper. And so in this video, there's just a piece of gel that's got these copper wires in them. And when you apply a positive voltage, that generates copper ions, which generates the stress necessary to bend these things. And I admit that this demonstration is a little bit slow and maybe not compelling, but the point is we're able to use electricity to control the motion of a gel that's very, very soft. So when you reverse the electric field, that creates opposing stress, which causes this thing to open. So with that, I'd like to conclude and tell you that, well, hopefully remind you that I've shown you these different ways to convert 2D surfaces into those with either 3D shapes or some kind of actuation or topographical changes. And then most of what I've shown you was using inkjet printing combined with light or some source of energy to cause folding, including like sequential folding and more complicated shapes that are useful for things like grippers and corrugated structures, such as the one shown here, where this is one of my graduate students standing on this platform made out of these really thin materials. This work was done in collaboration with a lot of people, and I've mentioned many of them as we went, but one of them I would like to particularly point out, which is Jan Genzer. He's one of my really good friends and colleagues, and he deserves a lot of credit with this work. I believe I've mentioned these other folks, but these are students. And, one of the things that was really special about this project was that we involved a lot of high school students and undergraduates. So at one point, some of these students were actually taking these light bulbs home and doing experiments in their apartment or their family's house. And so they really are very easy to do. And we're really lucky that we had a great group of students to work with. If you're interested in learning more, there's a couple of resources that I think might be worth your time. One is a review that was published a few years ago, and we're trying to be funny with our title. So you might recognize the title like To Be or Not to Be. It's like Shakespeare. So 2D or Not 2D, it's easy to remember. And then there was a special issue that we had in Materials Research Society Bulletin a few years ago that talks about some of these things. So I would like to take questions, but if you don't mind, I think I still have another minute or two. I would be really sad if I didn't, first of all, thank you for this entire week, for being here and for just the amazing questions and your attention and your energy. And I'm just, it's kind of sad that I'm not meeting you in person, but I hope that we'll find some excuse to get together. And I know that a big chunk of the audience here are students, and I would really like you to consider applying to our graduate program. And if you don't mind, I've just got a couple slides to tell you about what makes this place really special. So first of all, and I've told you this before, but just as a reminder, we are in the state of North Carolina. And if, this is a small portion of the United States, you can see here's Atlanta, Washington, D.C. would be up here. New York would probably not be on the screen, but maybe somewhere up here. And then Florida is down here. So we're obviously on the East Coast. And one of the things that makes Raleigh, where we live, very special is that you can go this direction to the west and see beautiful mountains. They're called the Blue Ridge Mountains. Sometimes they're called the Smoky Mountains, depends where you are in these mountains. And if you drive this direction, we have really beautiful beaches all along this coast. And we have really special beaches out here that are called the Outer Banks. So it's, you have access to a lot of natural beauty in this state. And then the city where we live in Raleigh, it's very special because we have a lot of universities here. So there's NC State, University of North Carolina, Duke, and they're all very, very close together. And so as a result, we have really good culture here. Our city is about 1 million people, and we have a lot of, plays and concerts and sporting events and stuff that come through our city. In terms of our university, we're big. I know you probably don't think in terms of acres, so I'm not sure how to convert this into something meaningful, but this is a really big campus with about 35,000 students. So it's quite large. And I mentioned earlier, but we call the Wolf Pack. So this is Mr. Wolf and this is Mrs. Wolf, and they're married. They don't have any babies, but they're married. And we're very lucky. We have very nice campus. So this is a brand new student center that was just built last year. This is what it looks like on the inside. Actually, if you look carefully, this is a wolf right here. And we have a brand new gym that is so new that I actually don't have a picture of it. This is just a architectural rendering of it, but it's quite nice. As you know, it's kind of a unique thing in the United States that sports are a really big deal. So this is our American football stadium. And you can see it's quite big, maybe holds 60,000 people. And on Saturdays, this is a really fun place to be when there's not COVID. And we also really like basketball here. And so this is our basketball arena. And you can see it's also very large. I think it holds 18,000 people. And so this is also very popular. And actually our basketball team is pretty good. And we're starting, I think, in 2 weeks. So they'll start their season. On our actual campus, this is our bell tower. You can see there's a lot of trees. It's quite beautiful. And then this is our campus, Centennial Campus, where we are. It actually has a golf course that's designed by Arnold Palmer, who's a famous golfer. You can see downtown Raleigh with the cranes where they're constantly building new buildings. In terms of our department, it's big. We have about 150 graduate students, and it's quite diverse. So this is a picture of one of our first year classes. You can see that there's people from all over the world. And we would love to have some people from Mexico and other parts of South and Central America. We have a very friendly department. I'm going to show you a couple more pictures in a second. So the students do a lot of social activities. This is our actual building where we are. This is another picture of that building. So it's relatively new and quite nice. We are on a part of campus that's called Centennial Campus. This is an aerial view of that campus. So our building where I am is in this building, but these are all engineering buildings. These are dorms where students live. And then this is a really amazing building. It's actually our library. This is a picture of it. And it's amazing. And I'll show you another couple of pictures of it, but it's amazing because it actually has robots that get books for you. And I'll show you, I think I have a picture of it that I'll show. You might notice that a couple things. One is there's a lake here. So we're right on Lake Raleigh. So it's again, quite beautiful. There's trails for running and exercise. And there's a space here for that you can see is missing. It seems like it's missing a building. Well, that building is just finished, and this is what it looks like. So we have a lot of exciting new things that are happening here. Now I want to tell you a little more about this library. This is just our engineering library. We have another library on our main campus. So this is just for engineering. And what makes this special is normally in a library, there's a lot of wasted space with the books taking up a lot of room. Well, in this library, all the books are actually in this basement. And there's a robot that will go and get the books. So this is the basement of the building. And you can see it doesn't look like a normal basement. It's quite colorful and nice. These containers here can have all the books, and there's actually a robot that will go grab those containers and bring the book to you. So it's quite modern and exciting. And one of the consequences of putting all the books in the basement is that it has a lot of space, really nice natural lighting space for students to study and to work together. So we have nice facilities. We live in a very nice part of the country. I think Raleigh is ranked #1 or in the top 10 of places to live in the entire United States. But what really makes our department special is that it's very friendly. So this is a picture of our faculty. These are some of our graduate students. They were playing a game called Broomball. It's a hockey game. So you see some of them are wearing knee pads. And they do a lot of social things. So they play games, they go to the beach, they go to the mountains, these kinds of things. Okay, so it's a friendly place. Probably the most important thing, though, I want to tell you something that a lot of students don't realize, and it kind of makes me sad that students don't know this, but we support all of our PhD students. So if you come here, we will pay for your tuition. We will pay for your benefits, like your health benefits, your whatever, your teeth, your doctor's appointments. We will pay you also a stipend, and it's about $30,000 per year. So we support all of our students throughout their PhD. And so you can come here and not go into any debt in terms of like paying for your education. So that's all I have, except I have one recorded message. So there's one of my colleagues is actually from Mexico, and I asked her to record a greeting. And I really hope she's not talking about me because it's in Spanish. So you have to tell me. Let me see if I can get it. So this is a professor in our department, and she's just recorded a greeting for you.
Hola, ¿qué tal? Muy buenas tardes o buenos días a todos los que están viendo este video, en especial a los estudiantes de pregrado que están involucrados en esta escuela. Mi nombre es Adriana San Miguel, soy...
Let me try this again.
Están involucrados en esta escuela. Mi nombre es Adriana San Miguel, soy profesora asistente en el Departamento de Ingeniería Química y Biomolecular en la Universidad de NC State, North Carolina State University. Y los quería invitar a que exploren la oportunidad de hacer un posgrado, un programa de doctorado o de maestría en el extranjero, en específico en nuestra Universidad de North Carolina State University. Tenemos muchas áreas de investigación muy interesantes, desde materiales, catálisis, energías renovables, y también en biología, como en mi propio laboratorio investigamos degeneración y envejecimiento en gusanos usando métodos de ingeniería para adquirir información pues rápido de imágenes del microscopio. Y pues estamos localizados en una ciudad llamada Raleigh, en Carolina del Norte, que es un área muy buena para vivir, y les invito a que vean nuestras páginas de internet. Si tienen cualquier pregunta, no duden en contactarme. Mi correo electrónico es asanmiguel@ncsu.edu. Y muchos saludos.
All right, so that's all I have. Thank you for indulging me, and thanks again for your time and for having me here. And I'd be happy to answer any questions that may have come up during my talk or about our graduate program or anything that you saw this week. I'd be very happy to answer.
And many thanks, Michael, for your presentation, and not only this, but all three in total. We have some questions here in Zoom, and the first one is Carla, please.
Hello. I have the doubt about if you use more localized lasers to make the patterns in the polymers, and maybe there are smaller, or I don't know. You explain about light bulbs, but not about lasers.
Yeah, so that's a good question. So let me see if I can find it. So we did use lasers, but oops, I think I went past it. So this is the only thing that we've done with lasers. And in this video, there is a laser which is being focused using these lenses, and it's being focused onto the sample. So I'll show the video. So basically the laser here is delivering energy to the sample. Now, one of the things that I'm interested in, or have been interested in, and we haven't really pursued, is if we can, because of the lasers can be focused down into a small area, that you might be able to scale this down. So right now, the materials that we're using, you can see that they're on the length scales of like centimeters, or maybe as small as millimeters, but pretty big and relatively thick. So if we could be kind of interesting to try to scale it down and try to make the hinges smaller. The tricky thing is when you make things really thin, you still need to be able to generate a thermal gradient through your material. So if you shine the laser here, you need for this to work, at least by this mechanism, you need the top part to get hot and the bottom part to stay cold or not as hot. And so as you start to make these things thinner and thinner, it does not work quite as well.
And I have another question about, you show a thermal experiment about the wrinkles. Have you made some thermal or mechanic modeling?
Yep. Well, we have not personally, but you can. But yes, people have, and you can predict the wavelength, which is the distance between these peaks, based on the modulus. You're testing my memory here. I don't remember exactly, but I think it's the modulus of the two materials. And yeah, I don't remember the exact relationship, but I think it's something to do with the ratio of the modulus. It's either to the 1/2 or the 1/3 power. I don't remember. So, and then the other thing that matters is the thickness. Let me go back to this cartoon, this one. So the things that matter in terms of dictating the periodicity are the thickness of this rigid layer, which I haven't labeled, but people would usually call that H, and then the modulus of the substrate and the modulus of the top layer. So to get the wavelength to be smaller, you would want this rigid film to be thinner. And the idea is that in terms of bending energy, the thinner that this film is, the easier it is to bend. So if you think about it, like the minimum energy really for any kind of bending would just be one mode like this. But if you want to have multiple modes like that, that's gonna occur here because that film is attached to that substrate. And so if you think about like kind of what's happening, you're doing two things that are sort of in competition with each other. One is you're bending these films, which is dictated by its modulus and its thickness. And then you're also distorting the underlying elastic material. So there's also some elastic energy. And so, I'm sorry, I don't remember the exact scaling relationship, but it's something like the ratio of the modulus to either the 1/2 or 1/3 power multiplied times the thickness, and that gives you a rough approximation of the periodicity. So it's not a perfect model, but it's like a scaling relationship.
Okay, thank you.
Yeah, thank you. Great question.
More interesting. You're talking all the way. Thank you.
Thank you.
Arnoldo.
Well, thank you so much for your presentation. I'm in first grade, but I have big plans, and thank you for showing your university.
Great.
And well, my questions are, what kind of things did you use for the experiments with different colors, and in general? And if do the results depend on the type of thing you use?
Okay, so the first question was like what kind of experiments we did. For that, they were pretty simple. So we just looked at the absorption of light based on the ink. And believe it or not, one of the trickiest parts, maybe I can go to the slides. Let's see. Yeah, here it is. One of the trickiest things for us was, and this sounds really kind of embarrassing and silly, but actually controlling the color. Because if you tell your printer to print like yellow, for example, then if you actually look at it under a microscope, the yellow color is actually a combination of yellow with a bunch of like pink dots. And they do that because it makes it look better to your eyes. And so from like a scientific, like we wanted to do this in a very systematic way. In our printer, I think there's like 4 different colors in the actual printer head. And we had a really hard time actually just getting pure colors to be printed onto the material. So that was like actually kind of just a silly thing, but we wanted to be able to correlate the color, the way that it absorbs the light, and then use that to get the thermal information about the sample, about how hot it's going to get. And so that was like kind of the main focus of that work, is just showing the principle. I think you had a second part of your question, but maybe I answered it already.
Yes, it was that the results depend on the type of ink you use, the composition of the ink.
Oh, yeah. So it does, only in the sense that it can impact the way that it absorbs the light. So, you know, in inkjet printer, the way that we're doing this, just inkjet, it just puts down little dots of ink. So even something that looks black, when you look at it under the microscope, it's actually like little dots of black. And so, you know, that's, when you look at it with your eye, it's fine. But if you think about what's happening in terms of the physics, when you shine the light, it's only getting absorbed where there's black.
Oh, thank you. And well,
You're welcome.
another question that it's not related to the first one is that, in your opinion, in a new future, how can we apply these materials?
So most of what I showed you today is just using polystyrene, which is, it's an okay material. You know, it's used for things like Petri dishes and styrofoam cups and some other consumer goods, but it doesn't have great mechanical properties. It's kind of brittle. So the materials that we use here are mostly chosen because they're easy for us to get. And, you know, to really use this for anything practical, I think you'd have to explore other polymers, like engineering type materials like polycarbonate or something like that. So with that in mind, you know, if you can imagine taking the principles that we showed here and extending it into better materials, then, you know, there's kind of some of the things that I mentioned at the beginning, which is making electronics in 2 dimensions and then having them assemble into some shape. Could be something simple like, you know, you're shipping something, and it could be like, say, like a satellite or something that you're sending into outer space that can ship compactly and then assemble into some 3-dimensional object. And I think, you know, in some cases it's also unfolding, where you have some object that can then go back to being flat, or go from either a compact state into a big state, or a big state into a smaller state. I don't know that there's one I would call like killer application. I think, you know, from what I've seen, the probably the most compelling applications just in general of folding and origami are things like in space, using an outer space, where you want to ship something like, say, like a solar cell, you want to ship it very compact, and then when you get to outer space, you expand it. So that's, you know, that's one example. They're not using these materials that I showed you, so it's a different mechanism, but anyway, they're still using folding and origami. I think another one that comes to mind that's just, you know, it's actually being done is stents for your heart. So if you need to have surgery and you put a stent into your blood vessel and have it expand, those also use some of these principles of shape change and origami. For me personally, I'm sort of more interested in like the electronics. So trying to make something in 2D and then assemble it. So that's some of the work that we're still doing on this, but I don't know. I mean, I think if I were to be a little bit self-critical, I think, you know, the answer could be that this isn't useful for anything. But I think aspects of it, I believe, could be used.
Thank you.
Yeah, thanks a lot for this great question.
In YouTube, there is one question that I guess the answer. Jorge Salaiza is asking, where will you recommend to be studying nanomaterials and their usage?
That's easy. NC State. Well, I don't know. There's many good schools. I guess you're probably referring to graduate programs, but we do have good nanoscience. And actually, if that student would like to contact me, I can maybe try to learn more about their specific interests and try to point them in the right direction. Because there's lots of good programs. I mean, I'm kidding. NC State it would be a great place, but there's lots of good programs that you might consider.
Leo Sina is asking if is there any currently available funding for internships or specific projects?
So there's kind of two parts to that question. The first is if you're considering graduate school, like I said, we do support all of our graduate students. And so if you were to apply to our graduate program and get admitted, then you would be supported financially and you'd have a project and everything would be good. If you're thinking more about like a summer internship or something like that, as far as I know, I don't know that we have any programs set up to support students in that way. What has been done, and like I've done it many times in my lab, is if you can make an arrangement with an individual professor, maybe they either have funds or maybe you even would self-fund yourself to come and have some kind of like a study abroad experience. So I've done that in my lab. I've done that with many people. So I've had students come for periods of time from, all over China, Korea, Singapore, India. Pretty much every summer I have a student that comes from India who's an undergrad that they come and they do research for a summer. So personally, like I like that because it's a great way for the student to come and travel and see a new place and meet new people and get some research experience. And then, for us, it's good because we like interacting with students, and maybe you decide you want to come here for grad school. So we definitely try to do that, but yeah.
Thanks. David Padilla.
Okay, hi. First of all, thank you for all the presentations. They are awesome.
Thank you.
My questions goes to about the process in which you use ink. Is there a form to make this process reversible? What I mean, first you bend the material, and there is a way to make it reversible.
Yeah, so that's definitely one of the limitations of this, is it's effectively irreversible. I mean, the reality is, yes, you can reverse it. So if you put one color ink on the top, you can get it to fold up, and then you have a different color on the bottom, you can get it to actually fold back down. But once it's folded, it's pretty much done, because the thing that's driving this is it's shrinking. So, it's a little bit like taking a rubber band and stretching it. When you let the rubber band go, it stretches back to its original shape, and it's not going to go back unless you physically pull on it. Now, that said, there are some polymers that are so-called shape memory polymers that can do, I forget what they call them. I think they're called two-way shape memory polymers, where they can bend in one shape, and then when you cool them back down, they bend back to a different shape. And so in principle, if you could use those polymers, and we haven't done it just because I think it's a little bit challenging, but if you use those polymers, you could reverse it. And the way that those work is they use crystalline domains that are in the polymer. So when you heat it, those crystalline domains will melt and the material will soften, and any sort of stress will cause it to bend. And then when you cool it down, the crystalline domains will reform and will push the material back into a flat state. So yeah, basically the materials I showed you today are you can unfold it one time and then that's it. But I think there is a path forward if you wanted to really do this. But you know, one of the other issues with these types of materials is they can't do a lot of work. So if you imagine you want this thing to fold and you want it to, I've got my phone here, you want it to do some work and pick up an object, it doesn't really work very well because you're essentially making it soft whenever you heat it. And so that's to me, that's really the bigger issue with these types of materials is not the reversibility so much, but the ability to do work.
Okay, thank you.
Yeah, sure. Great question.
Robin?
Actually, hello. Actually, it wasn't a question. I really love the university. It's like, wow.
Thank you.
Yeah,
Okay.
I really like it. Maybe we
good.
could see you there.
Please, that would be wonderful. We would love that.
Thanks.
Thank you so much. Thank you so much.
Mohammed?
Good evening, Dr. Michael. I do have a couple questions about applying for postgraduate student there. And is there an application fee for applying for postgraduate? And does it offer like the 30 grand after tax or before tax? And the other question, is it required to get a GRE exam or without any exam?
Okay, those are good questions. So I'll start with the last one. So for the GRE, we did require it up until last year, but now we are not requiring it. So that's good. So you don't have to take the GRE. Thank you for asking that because I forgot to mention it. That's good for students. The stipend is before tax. So, and it's actually more than what I said, but it's kind of a weird thing. We actually pay the students some extra amount because they have some fees that they have to pay. So I didn't count that, but I think we actually pay like 33 or 34,000, and then they use that money to help pay some of the university fees. But anyway, you would still have to pay taxes. But I think it's been so long since I've made that amount of money. But I remember when I was a grad student, like you basically don't have to pay taxes or very, very little because the amount is so low. There's something in like the United States tax structure. So depending on how much money you make, you fall into different they call it tax brackets, tax rates. And then I think your first question was about application fee. So the university does have an application fee, and I think it's $75. And before I became a professor, I didn't really understand these fees. I just want to let you know that those fees do not go to me or my department or anybody. We actually have what's called a graduate school, and they are the ones that like help process applications. And so those fees go to support the graduate school. I mean, honestly, when I see them, I think like, gosh, it seems like a lot of money because you're just like typing in information on these forms. But what the money's really paying for is to help all the operations behind that. So sometimes we get emails from students that say, can we get a waiver? And the problem is that somebody has to pay that money. And the question is who? Is it you, or is it me, or is it my department? So there's So the graduate school never comes back and says, "Oh yeah, you don't have to pay that." That said, if you have a financial hardship or something like that, and that's the only reason that you wouldn't apply, then reach out to me, because we'll try to help you. I don't want that to be the reason that you can't apply, but the kind of the flip side, just to maybe offer a different perspective, is that let's say it's $75 to apply, which again, it's not going to me. I literally don't see a penny.
I know.
But the flip side is that for us to support a graduate student, it costs us about $500,000 over 5 years, between paying for your stipend, paying for your tuition, paying for your benefits, paying for every chemical you use, your travel, like everything. And so it's quite expensive. And so for us, it's sort of like, well, it's a little bit of an upfront cost, but then once you're here, you don't have to pay for anything. So, but again, I don't mean to downplay it. $75 is still $75. And so, let me know if that becomes an issue, because I would like to help you.
No, it won't be an issue. Just another question. Can I ask you about your experience in Harvard University?
Yeah, sure. Yes, I did a 2-year postdoc there, so I wasn't a degree-seeking student, but I had a really good experience.
Yeah.
Was there something specific, or did you want me to just tell you a little bit about it?
Which group do you work for, and what did you research for? What did you research for? Like, what do you do? How many applications did you do for 2 years there? And what did you research? What was your professor there?
So I was there as a postdoc. So that was after I finished my PhD. I went there for 2 years, and I worked in the professor's lab named George Whitesides. He's pretty famous chemist. He's he does a lot of different work, and he's absolutely brilliant. And he was a really good mentor for me. He's older now. I think he's 80 years old, but just amazingly energetic and brilliant. His group is quite large, and I think he doesn't take graduate students anymore. I think it's just postdocs because of his age, and also just because of the nature of his projects. But there was two things that were sort of really special for me of that time in my life. One was that the group was very big, and so they worked on many different things, like crazy stuff, like the origins of life, assays for the third world, robotics, solar cells. It's just like so many different things. And so just within that group, I learned so much about different fields. And so, and the people in the group were really good. So I learned a lot also from the other students. So that was one thing. And then the other thing was that my advisor, Professor Whitesides, is a really good writer and a really good communicator. And he helped me become a better writer. I think I was already a decent presenter, okay, but I was just probably like maybe below average writer, and now I've improved a little bit. So it was a really good experience. And if any of you are thinking about going into like academics and becoming professors, I think an experience like that can be really good, because for me, it just broadened my horizons. And I know it probably sounds like way too much school, but it like, if it paid a little more, I probably would have done that the rest of my life.
I know. And your research work in Harvard was for like...
Oh yeah, thank you. Yeah, sorry, I forgot to answer that. Generally speaking, it was on unconventional nanofabrication, so making nanostructures in an unconventional way. So I did a little bit of microfluidics, a little bit of some other stuff, but the group that I was in was very collaborative and very focused on papers. And so, I'd have to go back and count, but I've probably in those 2 years, I've probably published like 7 papers or something. And it's not because of me being special or anything. It was just a really good environment for that and had a lot of help.
I know, thanks a lot, and a lot of greetings from me. I appreciate your presentation and appreciate your answering my question and my inquiries.
Thank
I
you.
followed your and subscribed your channel on YouTube, and I prefer the other students do the same and watch your videos. They are amazing video. I watched all your experiments there.
Thank you. Well, that credit goes to the students. They created those videos. I'm sort of like the associate director or something. Yeah, the students made those, and one of my students was joking that they need to have a master's in videography to graduate, but I never force the students to do that, but I think in some cases they really enjoy it because it kind of shows off their work in a visual way. So yeah, so I'm glad you liked them. Thanks a lot.
Hey, thanks a lot for your job and your presentation today. It was an amazing week, and we look forward to look for more presentation and for more work in future.
Thank you. Likewise, I hope we can stay in touch.
Okay, well, we are on time, but if you have some 5 minutes, there are some questions more.
Okay.
Okay, in YouTube, are asking about the cost of creating the materials like the glippers and the caliber or the width of and type of the polyester that you use because they want to try at home.
Okay, let me oops.
And also someone asked if you could share your applications for the students.
Okay, hang on 1 second. If I can do this quickly, I'll do it. I think it's this. These are this is the materials that we're using, and I'm sorry you're gonna think that we're like bad scientists for playing with children's toys. But when you buy these, they come in a package and they're just like clear plastic sheets. You can, if you email me, I can probably find a better link where it's less expensive, but you can see even this is not too expensive, but maybe I can send you, I actually have some instructions on how to do this, and I can send you, it's actually much, much cheaper, but this is just the first one I found quickly, and I'll put that into the chat. If I can figure out how to do it. Chat. Okay, so that's the link for that. All right, so that was one question. I'm sorry, what was the other one?
The other one was well, you already show us the cost, plus scissors and some other stuff. The lamp can be, you already show. So there is another question of a couple of questions from Pablo and then Jose.
Okay.
Hello, thank you for your presentation.
Thank you.
Yeah, my question is have you ever tried to use light and ink to make the materials rotate or vibrate?
That's a neat idea. No, we haven't tried that. Maybe you can try it and tell me how it goes. We've actually used these materials to do outreach events for children, and it's really fun. Like kids from like age 5 all the way up to 55. I think we've seen adults that really enjoy playing with these things, and I have to say, sometimes when we do these outreach events, sometimes the children teach us stuff. Like they do stuff that I would not have logically thought to do, but sometimes we see like really interesting shapes and stuff like that. So we've probably seen something like that in those outreach events, but we haven't done it kind of systematically in the lab. Yeah, thank you. It's a great question.
Thank you. And Jose, the last questions. this season, this lesson.
Hello, morning, Doctor.
Hi.
It's a really good.
Oh, thank you.
The question is it would be possible to model polymer sheets with wires like sandwich and current wires?
Yes.
For liquid metals.
For liquid metals. Oh, that would be cool.
Yeah.
Yeah, actually, where is it? Sorry. Shoot. This one. This example here, actually, this is not liquid metal, but they use joule heating, so it's using electricity. So there's no light. Each of these, I wish I could pause it, but each of these hinges actually has some metal or something that can cause it to get hot. So they're using electricity where we use light, but it's the same materials and same idea.
Okay.
Yeah,
this is a so they could control the blenders, no?
Mm-hmm.
Okay.
Yep.
Thank you so much.
You're welcome. Thank you.
Well, many thanks, Michael, for the presentation today, as well as for the course. And well, as you mentioned, we will find the time to invite you to come to Mexico, Morelia, and some other places maybe. So many thanks. We will we will send you this. I forgot the name in English. In this official document from the university, creating all this work that you do, and also some of this information will be available in Spanish in the chapter of the book that will be shared with you as soon as it is ready. So once more, thanks, Michael, sorry, and see you in 15, 20 minutes for the next and last session of today.
Thank you all.
Thank you. It's a lot.
Sí. Nos han preguntado sobre muchas gracias a las personas que nos siguen de YouTube, y en este momento vamos a cortar la transmisión y empezaremos en aproximadamente 15 minutos para la última plática del día de hoy y para la clausura. Muchas gracias.